Welcome students to this video. The topic will be about instruction pipelining. Some of you have already seen this topic in undergraduate course. However, I'm going to cover it anyways. For those who have not really seen it, they can study the video. So the focus will be on basic and intermediate concepts. We'll talk about advanced pipelining later in a later presentation. This is the outline of this presentation. Okay, in this video, I will be talking about pipelining basics. There will be a series of videos. I will be talking later about the MIPS 5-stage pipeline microarchitecture. I'll be talking about the different types of hazards that are faced by the designer, okay, when implementing the pipeline. These are structural hazards, data hazards, and control hazards. Okay, so let's get started, okay, with the basics of pipelining. Okay, so the first question that comes to our mind is, what is pipelining? Pipelining is a form of parallelism. Okay, people have been using pipelining for a long time. It appeared in assembly lines in the industry for more than 100 years now. So it is a form of parallelism. So the idea, if you have a task and you can divide this task into k subtasks, then you can execute these k subtasks on k different stages of the pipeline. If each subtask requires one time unit, the total execution time of the task will be k time units. But the idea is to overlap the execution. You don't really have to wait for one task to complete to start another task. So this is the difference between serial execution and pipeline execution. If you look at this slide carefully here, you can see that there is a difference between serial and pipeline execution. So with serial execution, you can see one completion every k time units. So here is my task. I'm going to use a pen tool. So this is my task. Okay, I'm going to write here task. So the task here will take k time units. So if you are using serial execution, then this means that you have one task completed every k time units. That's serial execution. On the other hand, if you use pipeline execution, once you have filled the pipeline, then you have one completion every one time unit. So after you have filled the pipeline, this task will complete. So task 1 will take k time units, but task 2 will take one extra time unit to complete. Then task 3 will take one extra time unit to complete, and so on. So one completion every one time unit rather than one completion every k time units. That's basically pipelining. Okay, so our focus here will be on a pipeline implemented inside the CPU. So this is an instruction execution pipeline. So the pipeline consists of k stages, and these are named S1 to Sk, as shown in this slide, at the bottom of this slide. Now you can see that in order to implement this pipeline, you need to have pipeline registers between the stages. All of these registers are connected to the same clock. So these are clocked registers. They change their value at the same edge of the clock at the same moment in time. So each register takes its output, it receives its input from the previous stage and provides its output to the next stage in the pipeline. Now it's very much desirable to have these stages to be balanced, okay, because if they are not really balanced, then the stage that has the longest delay will be a bottleneck. It will be a bottleneck in the pipeline, and it's going to increase the clock cycle. So the clock cycle here, or the clock period, is determined by the maximum stage delay. Let us take a look at the pipeline performance, the theoretical pipeline performance, when we compare it to the serial execution. So we can look at the delay in every stage of the pipeline. Let us define tau sub I, which is the time delay in stage S sub I. Now, what's important to us is the maximum delay at any stage, because the stage that has the longest delay is going to define the clock cycle. So we define the clock cycle, which is maximum tau sub I, and this is based on the longest delay at any stage. So the frequency is just 1 over tau. And now, once we have defined the clock frequency, we know at what rate, okay, the instructions are going to execute in the pipeline. Now, if we would like to find out the speed up, okay, the speed up of a k-stage pipeline versus serial execution, I have to divide the serial execution time in the clock cycles divided by the pipeline execution time in the clock cycles. So this is S sub k, which is shown here below. Okay, just here say S sub k. That's the speed up. So what is the serial execution in the clock cycles? The serial execution time in the clock cycles, we are executing n instructions over a k-stage pipeline. So if we are executing n instructions and each instruction takes k clock cycles to execute, from the time you fetch it until it completes, it takes k clock cycles, then the serial execution time will be n multiplied by k. That's the serial execution time. Now, how about the pipeline execution time in clock cycles? Well, again, we are executing the same n instructions over a k-stage pipeline. Initially, the first instruction has to go through the k stages of the pipeline, so it's going to take k clock cycles. So k clock cycles here for the first instruction. Now, once we have the first instruction has completed, the second instruction is just after it in the pipeline. So each instruction after the first one will require only one cycle to complete. Because of pipelining, the instructions are going to complete at the rate of one instruction completed every clock cycle. So the remaining n-1 instructions will require only n-1 cycles. Okay, so that's n-1 cycles for the remaining n-1 instructions. So in total, we have k plus n-1 cycles. This will be the pipeline execution time in the clock cycles. So if I would like to calculate now the speed up, so the speed up becomes the ratio of nk divided by k plus n-1. This is the speed up equation for a k-stage pipeline. Okay, that's the theoretical speed up. Now, typically k is small. If you have a 5-stage pipeline, then k is just equal to 5. Today in modern CPUs, you might have k, the number of stages, anything between 10 and 20 stages is typical today in modern CPUs. So k is a small, okay, n can become very large. For example, you might be executing billions, if not more, trillions of instructions. So if n is very large compared to k, then k plus n-1 is approximately equal to n. I can simply approximate this as n and ignore the k minus 1. So we can ignore the time to fill the pipeline, and we can assume that the pipeline execution time in cycles is simply equal to n, which is the number of instructions. So when you divide nk by n, you will get k. So for large n, the speed up is equal to k, which is the number of stages in the pipeline. And this is expected because we have k stages, and these k stages operate in parallel. So we expect the speed up to be equal to k, which is the number of stages in the pipeline. In this presentation, I will be talking about a simple 5-stage processor pipeline for a RISC-like processor, for example, like a MIPS processor. So I will go over the details of the data path and control, but this will be done in the next video. So there are 5 stages, and each stage will take only one clock cycle. So the first stage is called the instruction fetch stage. This is where we fetch the instruction from the instruction cache. Also, we select the address of the next instruction. It could be the next instruction in memory, or it could be the address of the target instruction for a jump or a branch if you are jumping or branching. The second stage is called the instruction decode stage. So during this stage, we decode the instruction, we determine the control signals. So here the control logic is going to examine the opcodes, going to examine the function code to generate all the control signals which are needed to control the execution of the instruction. At the same time, we can read registers from the register file. So this is all done during the same stage. So we decode the instruction, we generate the control signals, and in parallel, we can read 2 registers from the register file. In the third stage, we execute the instruction. So this is called the execute stage. So if you have an ALU instruction, we can simply execute the operation. If we have a load or store, we can use the ALU to do effective address calculation. So we can use the ALU to calculate the effective address that will be used to access the data cache in the fourth stage. If it was a branch instruction, we can execute the branch to determine the outcome of the branch. So we need to know whether the branch is taken or not taken, okay, during this third stage of the pipeline. And the fourth stage, this is called the memory stage or the memory access stage. This is needed by load and store instructions. So in this stage, we have the data cache. We access the data cache. Okay, so we can read or we can write the data cache during this stage of the pipeline. Finally, we have the write back stage. This is the fifth stage of the pipeline. This is where we write back the result into the register file. To understand pipelining, we should really visualize the pipeline. We have to understand really what's really happening in the pipeline at each clock cycle. So we can visualize how the instructions are moving in the different stages of the pipeline. So here's an example in which I have the 5 instructions in program order. So the horizontal axis is showing time in clock cycles, and the vertical axis is showing the program instructions. So the first instruction is a load word, the next one is add, then or immediate, then subtract, and store word. Typically we have, as I said, we have millions, if not billions, of these instructions, but I can only show a few, okay, when we would like to visualize the pipeline. So at a given clock cycle, we can see what's really happening inside the pipeline. For example, take clock cycle number 4. I'm going to use the pen tool again here. So that's clock cycle number 4. And you can see that during clock cycle number 4, the load instruction has reached the data memory stage. Data memory here means data cache, and instruction memory means instruction cache. So the load has reached the data cache. Okay, so it is reading the data cache. It's loading the data from the data cache. At the same time, we have the add instruction is being executed by the ALU. I have the or immediate reading the registers from the register file. It's being decoded also in the second stage of the pipeline. And I have the subtract instruction being fetched from the instruction cache. So, so 4 things are happening at the same time. Of course, in general, okay, we have 5 stages. 5 things can be happening during the same clock cycle. This shows the timing of the instructions. So I can actually draw, again, the horizontal axis is the time axis, which is shown in clock cycles. And the vertical axis is showing the instructions in program order. So this will show the instruction flow, okay, over the 5 stages. Okay, for example, you can focus on a given clock cycle, like, for example, a clock cycle number 5. You can see that we have 5 instructions. So as soon as we have filled the pipeline, you can see that we have 5 instructions in the pipeline during the same clock cycle. So the first load instruction is now in the write back stage. So I'm just writing the name of the stage. Okay, so the first load instruction is in the write back stage. The second load is in the memory stage. It's loading the data, it's reading the data from the data cache. The third instruction, the or immediate instruction, is in the execute stage. So it is being executed on the ALU. The next instruction, the subtract instruction, is still being decoded. It's in the instruction decode stage. And finally, the last instruction here, the store word instruction, is in the instruction fetch stage. It's actually being fetched from the instruction cache. Notice that some instructions might not require some stages. It's fine. Yani, for example, the or immediate can bypass the memory stage without doing anything. So you can see that here, okay, we are skipping the data memory stage, the data cache. So the or immediate does not really need to read or write the memory stage, so it can skip the memory stage. Similarly, the store instruction might skip the write back stage because nothing is written into the register file by the store instruction. Let us take a look here at an example of pipeline performance before I go into the details about how to, what is the data path and control and how to deal with the data hazards and control hazards. Before I talk about all of these topics, let me just show you a quick example about pipeline performance. So this example, we are considering a 5-stage instruction execution pipeline. It says that the instruction fetch, okay, to fetch an instruction from the instruction cache, it takes 350 picoseconds. So it's given here as 350 picoseconds. The same thing for executing. So this is the delay, okay, for the instruction fetch. The same thing, the delay in the ALU, and the same thing, the delay in the data memory access in the data cache, it's 350 picoseconds. So this is how it's given. Okay, of course, circuit designers have to look at the real delays inside these components, inside these different stages of the pipeline. It says that the register read and the register write, it's only 250 picoseconds. So to access the register file, it only takes 250 picoseconds. Of course, the numbers might be different according to the technology which is being used. Okay, but this is actually simple, okay, given like that in this example. So now let us actually compare single cycle versus multi-cycle versus pipeline execution. You can design your CPU to be single cycle. What it means is that every instruction will take exactly 1 clock cycle. That will be the single cycle CPU. The multi-cycle CPU, you can design the CPU in which each instruction will take a different number of clock cycles, and the idea is to optimize performance. So you can actually have one instruction taking fewer clock cycles and another instruction taking more clock cycles, depending, of course, on the latency of each instruction. And then finally, we have pipelines. Okay, so let us compare these 3 different organizations, these different ways of implementing the CPU. Now, in order to make this, to look at the performance, especially for the multi-cycle, I need to know what's the frequency of instructions. So it says, assume that 20% are load, 10% are store, 40% are ALU, and 30% are branch instructions. So I need this information. I need to know what's the frequency of my instructions specifically for the multi-cycle. Now, in order to solve this problem, okay, I need to look at the delay of each instruction. So every instruction has to be fetched. So it takes 350 picoseconds to fetch the instruction from the instruction cache. That is the given in the problem statement. Every instruction has to be decoded and it has to read, okay, it registers from the register file. So it takes 250 picoseconds to read from the register file. So while we are reading from the register file, the instruction is also being decoded. So I'm assuming 250, these 2 things are done in parallel, and it takes 250 picoseconds to decode the instruction, to generate the control signals. That's for the control logic. And at the same time, we are reading from the register file. It takes 350 picoseconds to execute on the ALU. That's the delay inside the ALU. I'm assuming simple ALU instructions. So there is nothing which is complex. For example, I'm not talking about like a divide instruction that takes longer to execute. So simple ALU instructions like a simple arithmetic like addition, subtraction, or logic operations. So these are really can be done very quickly inside the ALU, and the delay is really short, which is given here as 350 picoseconds. The access to the data cache, which is shown here as memory, that's the data cache. It's only 350 picoseconds, and the register write is 250 picoseconds. Now, depending on the instruction type, some instructions will take longer. Okay, they have a longer latency than other instructions. You can see that the load has a latency of 1,550 picoseconds. Now, why? Because it has to be fetched, it has to be decoded, it has to read registers from the register file, it has to execute. So here, ALU will be used for address calculation for a load instruction. Memory will be used, so the load need to access the data cache, and also the data has to be written back into the register file So all of these stages will be accessed, and therefore the total latency, if you add all of these numbers, you get 1,550 picoseconds. Now the store, okay, does not really need to write anything into the register file, so nothing is written here. Okay, so basically there is no need, okay, to write anything back into the register file. So we can reduce the latency of the store to only 1,300 picoseconds. Notice for ALU instructions, they don't need to access the memory, which is data cache, because they don't load, they don't store. So there is no need to access the memory. So therefore, the latency of a typical ALU instruction is only 1,200 picoseconds. Whereas in the case of a branch, there is no need to access the memory, the data cache, or to write anything back to the register file. So the latency of a branch can be reduced to 950 picoseconds. So this is a simple analysis, okay, for these different types of instructions. I'm looking here at only four classes of instructions. We might also have different classes, but they are not really shown here. For example, I might have floating point that might take longer to execute. I might have like multiply or divide instructions. These will take longer to execute, but I'm trying to simplify the problem statement here. Now, if I would like to use single cycle, just single cycle processor, then we have to fix the clock cycle inside the hardware. So how do I choose my clock cycle? Okay, in the case of a single cycle CPU. Okay, so how do I do that? Okay, so the answer is simple. Okay, in order to decide what should be the clock cycle, you have to go by the maximum delay. So the maximum delay is for a load instruction. So for a single cycle, I can choose, okay, my clock cycle to be 1,550 picoseconds. That's how it is selected, okay, for the single cycle. So we go here by the instruction that has the longest delay. In other words, in the case of a single cycle CPU, all the instructions, okay, will take as long to run, okay, so they will run at the same speed as the slowest instruction that exists in the instruction set. That's the problem. This is the major drawback of single cycle. Okay, it uses a very long clock cycle, and it will slow down the execution of all the instructions because the clock cycle and the clock frequency has to be fixed in the hardware. So therefore, it has to be at least, the clock cycle has to be at least 1,550 picoseconds, and therefore all the instructions will slow down the execution of all the instructions. We cannot change the clock cycle from one instruction to the next instruction in a program. That's not really possible to be done. So we fix the clock cycle, and we say that the clock cycle is 1,550 picoseconds for all types of instructions. That's for the single cycle. For the multi-cycle, I can choose here between 350 picosecond and 250 picosecond. So to fetch an instruction, it takes 350. Okay, to decode the instruction and read from the register file, it takes 250 picosecond. So therefore, we can say that what's the maximum, 350 or 250? It's 350. So let us choose the clock cycle to be 350 for the multi-cycle. Finally, so in the case of the multi-cycle, we can see that the load instruction will take 5 cycles because it has to be fetched, it has to be decoded, it has to use the ALU for address calculation, it has to access memory, and then it has to do register write. The store will take only 4 cycles. The ALU will take also 4 cycles, but the branch will take only 3 cycles. So you can see in the case of the multi-cycle, different instructions will have different number of clock cycles. That's the difference between single cycle and multi-cycle. Single cycle, it means that one cycle per instruction, even though that this cycle is very long. In the case of multi-cycle, different instructions will take different number of clock cycles, and this can vary. So the number of clock cycles, the CPI, okay, will be different in the case of the multi-cycle. Finally, we have the pipeline. Pipeline can use again for pipelining, we can use the clock cycle to be 350 picoseconds. So we have to decide between 350 and 250. So the longest delay at any stage is 350 picosecond. But because of pipelining, we don't really have to wait for the instruction to complete to start, okay, the fetching of the next instruction. So this can reduce the CPI in the case of pipelining. Okay, so the difference between multi-cycle and pipelining is that multi-cycle is still serial execution, whereas pipelining, okay, it's not serial. So we don't really wait for an instruction to complete to fetch the next instruction. So if you would like to look at the numbers now, this is shown here in this slide. This is actually shows single cycle execution. Every instruction will take 1,550 picoseconds. Now it is single cycle, so we calculate here the longest delay, okay, which is 1,550 picosecond. The CPI is equal to 1. That's why it's called single cycle. Okay, so every instruction will take 1 clock cycle. This is nice, but the problem is the long clock cycle time. So the long clock cycle is going to make the execution very slow. On the other hand, multi-cycle, you can have different instructions, they taking different number of clock cycles. You can see the load taking 5 cycles. The ALU will take 4 cycles and the branch 3 cycles. Okay, so different instructions have different number of clock cycles, but the clock cycle is reduced to only 350 picosecond. Now, in order to calculate the CPI, in the case of the multi-cycle, you have to look at the frequencies. Okay, so 20% of the instructions are load, so I multiply 5 cycles by 20%, which is the 0.2. 10% are store, so I have to multiply 4 cycles multiplied by the 10%. And 40% are ALU, so I multiply by 4 cycles, and 30% are multiplied by 3 for the branch instruction. So this will give me, okay, an average CPI, which is 3.9. Finally, for pipelining, this is pipeline execution. You can see that how pipelining, okay, reduces the overall execution time of the program. You don't really have to wait for one instruction to complete to start the next instruction. So the clock cycle is again 350 picosecond, the same way that we have obtained the clock cycle for the multi-cycle. But the interesting thing is that the average CPI can be reduced to 1. And the reason why the average CPI can be reduced to 1, because we have 1 instruction completed every cycle. Of course, we are ignoring the time to fill the pipeline, because we can actually have a very large number of instructions to execute. So if you ignore the time to fill the pipeline, then that's the average CPI. It's actually just one instruction completed every cycle. So in summary, single cycle, the CPI is equal to 1, but the long clock cycle is 1,550 picoseconds. So you can look here at the time of each instruction, which is 1,550 picoseconds. For the multi-cycle, okay, we have seen that we can choose the maximum delay at any stage, which is 350 picoseconds. But the problem is that the average CPI is 3.9. It's worse than the single cycle. So if you multiply 350 by 3.9, you get this number here, 1,365 picoseconds. That's better than the single cycle. It's better than 1,550 picoseconds. If you divide, you get 1.14x. In other words, the multi-cycle is faster than the single cycle by this factor. It's 14% faster than the single cycle. Finally, for pipelining, we have reduced not only the clock, but also the CPI. So the pipeline clock cycle is only 350 picoseconds, which is the maximum delay at any stage. It's the same thing as the multi-cycle, but the average CPI is reduced to 1, because 1 instruction completes per cycle. So therefore, the average time per instruction is only 350 picoseconds. And if you compare it with a single cycle, you divide 1,550 by 350. This will give you 4.43x. It's more than 4.4x faster than the single cycle. And it is 3.9x faster than the multi-cycle. So this is the benefit of pipelining. This is why people today, when they design their CPUs, they design, okay, so all the CPUs today are pipelined. Okay, no one actually uses the single cycle or the multi-cycle. Okay, so multi-cycle was used in the past, but today people use just pipeline CPUs to make the program to run faster. You can actually get a much higher speed up, okay, over single cycle. You can actually get the speed up, okay, which is over single cycle and multi-cycle by using a pipeline CPU. So in summary here, pipelining does not improve the latency of a single instruction. It improves the throughput. Okay, so the instructions are initiated and completed at a higher rate. In fact, the latency of a single instruction is still the same. Okay, so the instruction has to go through all the stages of the pipeline. So so pipelining does not really make latency better. Okay, so what it is doing is that it's initiating and completing instructions at a higher rate. That's what pipelining improves. It improves the throughput, the rate at which we are completing instructions. If you have a k-stage pipeline, you can have k instructions. Okay, if you fetch one instruction every cycle, you can have k instruction in the pipeline at the same time in parallel. So you can have now, we are using multiple hardware resources, which are the stages, the k stages in parallel. And the potential speed up is the number of pipeline stages, which is k. However, we might not really achieve k, as we have seen in the last slide. We have achieved a speed up which is not 5x. We have achieved only 4.43x, as we have seen in the last example. And the reason is that the stages of the pipeline might be unbalanced. If we have unbalanced delays in these different stages, this will reduce the speed up. So for this reason, it is very much desirable to have these stages to be balanced so that to achieve a higher speed up. So if you have one stage which is slow, sorry, if you have one stage which is slow, this is going to reduce the clock frequency, is going to increase the clock cycle, okay, and reduce the clock frequency, and this would result in a reduced speed up. Also, we have the time to fill and drain the pipeline. We're ignoring this time, okay, so once you have filled the pipeline with instructions, then you get one instruction completed every cycle. But if for some reason you are actually draining the pipeline and refilling it, and you do this constantly, then you might reduce the speed up. We'll see later when you have hazards in the pipeline, then sometimes you have to drain the pipeline and refill it, and this might impact the performance of the pipeline. In the next video, I will be talking about the 5-stage pipeline microarchitecture. We'll go over the data path and control. I will also be talking about structural hazards. Okay, so thank you for watching. I will see you in the next video.